We'll start our consideration of trends of the periodic table by looking at effective nuclear charge, and we'll look at the trend of all of the things we're considering, first of all, as we move across the periodic table. So we're starting by looking at Z effective, effective nuclear charge, and as I go left to right across the periodic table, I keep adding protons. The size of the atom doesn't really change because I'm not adding energy levels. I'm adding protons in the nucleus, I'm adding electrons in the current available energy shells, but I'm not adding energy shells. So, as I add protons, the effective nuclear charge keeps increasing. The pull that those outer shell protons feel gets bigger and bigger as I go left to right. So, moving left to right across a row, effective nuclear charge increases. If I look at atomic radius next, as that effective nuclear charge increases, it pulls on those outer shell electrons. Because I'm not adding energy shells, and because the pull keeps getting stronger, those valence or outer shell electrons keep getting pulled closer and closer to the nucleus. So what that does is that makes the radius smaller. So as I go left to right across a period, the atomic radius will decrease as I go left to right. Now there are some glitches along the way, and we'll talk about that in a little bit. But in general, the trend is radius decreases. The next thing we'll look at is ionization energy, the amount of energy needed to pull an electron off a neutral atom to make it positive ion, or to pull more electrons off atoms to continue to make them more positively charged. Because the effective nuclear charge is increasing, because the radius is decreasing, those valence electrons are getting closer and closer to the nucleus. That's going to make it harder to pull those electrons off. So it's going to require more energy. So as I go left to right across a period, ionization energy will increase as I go left to right. Electron affinity is the amount of energy involved in adding electrons to neutral atoms to make negative ions. Again, more Z effective, smaller radius. It's easier to pull those electrons on as my effective nuclear charge increases and my radius decreases. So just like ionization energy, as I go left to right across a period, the electron affinity is going to increase as I go across. If we take a look at the trend of these four things as we go down a group, we'll start with effective nuclear charge. As I go down a group, again, I keep adding protons. So because I keep adding protons, the effective nuclear charge is going to increase. So going down a group, effective nuclear charge increases as I go down. Atomic radius is governed primarily by adding energy shells. So as I keep going down in rows, I keep adding energy shells. So the more energy shells I add, the bigger the radius is going to be. So as I increase rows, I increase radius. So going down a group, the atomic radius will increase as I go down. Ionization energy and electron affinity. As I go down a group, both the effective nuclear charge and the radius increase, but they don't increase at the same rate. And so it turns out that even though they're both increasing, those electrons, those valence electrons, because they're further from the nucleus, more importantly because they have so many electrons between them and the nucleus shielding them, the ionization energy and the electron affinity are actually going to decrease as we go down a group. And so there we have the four major trends, both across a period and down a group. And let's take a look at some of these in a little bit more detail now. Look at this ionization energy chart. If we take a look at the elements in the third row, so we start with sodium. Ionization energy for sodium is pretty small. Then it jumps up to magnesium, but then we jump down to aluminum, up for silicon and phosphorus. It drops for sulfur, back up for chlorine and argon. So we need to be able to explain why it drops from magnesium to aluminum and why it drops from phosphorus to sulfur. What's going on there? If we think about it in terms of electron configuration, magnesium has a full s orbital, so it's very stable. It takes more energy to pull electrons from stable configurations than from unstable configurations. Aluminum has one p electron, that's it. Full s electron orbital is hanging out there. So, because aluminum is less stable, it only has a single p electron, it doesn't take as much energy to pull that outermost p electron off. So its ionization energy is lower than magnesium's. Same is true from phosphorus to sulfur. Phosphorus is a p3 electron configuration, half-filled p orbital, pretty stable. Sulfur is p4. We've got one more electron beyond half-filled, so it's less stable, Therefore, that means it takes less energy to remove that extra fourth p electron from the orbital, and therefore its ionization energy is lower. And we see that pattern as we go across the periodic table for each row. Some jumps are much more significant than others. The D block to gallium is a huge jump, as is cadmium to indium. The other pattern that we look at is vertical. What happens to each of these four things as we go down a group? Effective nuclear charge increases as I go down a group. Why? Because I add a lot more protons as I go from one row down to the next, and the radius of each energy shell really doesn't increase that much. Remember, as I go up in energy levels, the distance between each successive energy level gets smaller and smaller and smaller. As I go down a group, the ionization energy is going to decrease. Even though those radii don't get much bigger, they do get bigger from one energy shell to the next, so the electrons being further away are easier to remove. Same is true with electron affinity. Those electrons, those outer shell electrons, are further from the nucleus, so the pull on them isn't as big. So electron affinity, like ionization energy, is smaller as I go down a group. Because I'm adding energy shells, each energy shell has a larger radius. Atomic radius increases as I go down a group. If I look at a periodic table that has the radii in the blue and the gray, our blue is atomic radius, yellow is atomic radius. Blue are the atoms that will form positive ions. So I start on the left and I work across to the right. The numbers in each of the boxes are the radii in picometers. So if I look at the fourth row, I go from potassium to calcium to scandium. Significant drops from potassium to calcium. Not quite as big a drop from calcium to scandium. Then if I look at the D block, going from one end of the D block to another, the change isn't that great, especially for those middle elements. Then I get to the end of the D block, I go from zinc to gallium, not much change. And then the radius starts dropping again, as I would expect when I'm dealing with those p electrons, the valence energy electrons. It gets smaller and smaller until I finally get to the noble gas configuration, full orbital. All those electrons squeeze into that space actually have maximum repulsion, and so that actually balloons the orbital to a larger size than when it only has 7 electrons. So the radius of krypton is actually significantly larger than the radius of bromine in the fourth row. If I take a look at the ion radius compared to the atomic radius, positive ions, I'm removing electrons. Essentially, I'm removing the whole outer energy shell when I'm removing those electrons. So the radius gets much smaller. Nonmetals generally form negative ions. So when I'm adding electrons to form the ion, I'm giving it a full octet. Well, neutral atom full octet, the radius gets bigger. So imagine what happens when I have more electrons than I have protons. The radius is going to get huge compared to the atomic radius because I have all those electrons. I have an octet of electrons in that outer shell, and I don't have as many protons to pull on them. And so those radii, those ionic radii, just balloon up extensively. So this takes us through Chapter 7. There's an awful lot of information here, so we need to make sure that we can sort it all out and figure out how to master it.